we've got our functional groups. So in theory, you guys should remember your functional groups. If I start asking you what's an alkane look like, what's an alkene look like, you should start being able to draw out example structures for all of those, okay, for all of these that are up here. As far as what you're responsible for naming for the exam, the alkanes, absolutely. The alkyl halides, I won't push on the nomenclature yet, but you guys should be familiar with naming those anyway, so you get a little bit ahead on the nomenclature. The rest of them, we'll talk about them when we actually get to them. So ultimately for nomenclature for the next exam, it's all about the alkanes. Okay? So your meth, eth, prop, bute, pent, hex, and then all the different combinations of putting the things together. Okay? So as far as our nomenclature rules, we did walk through a bunch of these. Find that longest continuous chain. I'd highly recommend that you circle it so that you now have it labeled. So that way you can then clearly identify what things are substituents attached to your main chain. So it'll help you process the rest of the problem. Okay? The suffix name, the only one you guys are really concerned about at this point in the semester is going to be the alkane or the ANE ending. As we move through, you'll start seeing all these other ones show up as well. Okay? You'll number your carbons according to placing, giving your substituents the lowest total number. Name your substituents, number them, put it all together, and you've got your overall name. Okay? As long as you follow the rules, it goes the exact same every single time. So you should end up getting the same name regardless of what the compound looks like or how it's oriented in space. Remember, watch out for IUPAC versus common names. Okay? So we ended with Newman Projections on Monday. Okay? So this is where a model kit can come in handy. I didn't do a very good job with that one. Okay, so if we take a look at an individual model, okay, and if we tried to draw this out, okay, we would attempt to put it together. So let's see if I can do this without it spinning on me. Okay, if we were going to draw this on, what is that, your right-hand side, let's see if I can do this while holding and drawing. We've got a green carbon atom, or is that blue? That looks blue. We've got our carbon atoms that look like little knot star things. Okay? We've got purple bonds going directly up on either side. Let's go ahead and show our purple. And you'll notice it's not perfectly straight up and down. Okay? So when I say up, really all I'm referring is in that up direction and in the plane of my paper. So where I would actually be drawing things. It's not coming at you. It's not going away from you. Okay, so we could draw on those purple bonds going up away from it, okay, either direction. Okay, the next part, we'll go with orange for our yellow bond. This would be what, your left or right side? To your left side? Okay, let's see if I can do this right. Our yellow bond, which I'll draw in as orange, okay, is aimed where? Above or below our carbon bond? Below, and it's aimed towards you. How do you represent it being aimed towards you? A wedge. So we would draw it, come on, with our wedge coming at you, okay, on the left-hand side. What about the other yellow one? It's aimed away from you on the other side. How do we represent that? With the dash. Again, that's below our carbon-carbon bond. Okay, everybody see that? We can then go through and do our green atom, or our green bond. Our green bond is going to take up the rest of it. The one on your right is aimed at you, so we can go through and show that wedge. Sorry. The other green one is aimed away from you. Can draw that one in. Okay? So that is now a valid representation of that three-dimensional model. We've used wedges and dashes to imply some of that not stereochemistry, but the three-dimensionality. So it allows us to see it a little bit better. Okay? One of the things that we said was a repercussion of sigma bonds, or single bonds, is that these bonds can freely rotate. And if I rotate it, and now, stop it, and now I try and draw it, does it look different? Yes. Okay, so I'm going to attempt to real quickly draw that one out. Okay, if we go through, we still have our carbon running through the middle. Our purple bonds are now on opposite sides. Let's go with our orange. Our orange are now both aimed away from you. The one on your left is aimed up. The one on your right is aimed downwards. Let's see if I can do that right. I may have just done this mirror imaged. Did I do it mirror imaged?
No.
And I said away, didn't I? I blame the pizza people for confusing me. And then we've got our green ones. Okay, one's aimed up towards you, and the other one's aimed down towards you. Okay, so we get two equal representations, okay, or what we might envision as being equal representations of the same molecule. Okay, all we've done is rotate that bond. And when we look at those line angle drawings, assuming we can interpret them because they are a bit messy, okay, we might not notice any real difference between them. Okay? And that's kind of what they thought until Newman came along and said, well, instead of looking at it from the side, I'm going to turn it. Okay? And look at it from the ends. And now when I go through and look at it from the end, we're going to look at it from this end. We'll discuss that in a second. Okay? Our purple bond is aimed down. So first off, which projection do we have here? Top or bottom? Which one am I trying to draw? Top or bottom? It's the bottom one. Notice the purple bonds are aimed opposite directions. If we turn it the other direction here, where's your purple bond? The front purple bond? Okay, it's now aimed down. It is technically aimed at you. If you looked at it from the side, you might see that it's aimed at you. That would make things really confusing to look at with adding wedges to this already cramped structure. So instead of doing wedges, I'm just going to go through and color it. So there's our purple bond. Our other purple bond is attached to the carbon in back. Okay, aimed above. Okay, we could then go through and identify the other bonds in here. Our orange ones. Okay, the one in front, color, dang you, is aimed up, and the other one is aimed down. If we look at our green bonds, okay. If we try to make our top or our other Newman projection, what we could do is rotate, and now we'd be looking at where all of those bonds are eclipsed, okay, or overlapping each other. All we're trying to do is look at those different things. And so Newman came along and said, okay, that's fine. I don't think those are equivalent. Okay? When he's talking about equivalent, he's talking about energy. This conformation, if we look at it from the side, is different energy from that conformation. The question becomes is why? Well, Newman went through and said, because you're looking at it wrong. Look at it from the end. When you look at it from the end, each of these lines represents a bond, which is electrons. All electrons want the most space possible, so they're going to try and repel away from each other as much as possible. These electrons may be a reasonable distance away from each other, but if we spin that back carbon, I can give it that pair of electrons a little bit more breathing space. That extra space lowers the energy of the overall structure. If the energy changes, we have a different reactivity. Okay? So we need to be aware of that different drawing or that different representation of the structure, because that can start to reveal different possible reactions. Okay? And that's ultimately what Newman projections are all about. Okay, how easy was that to understand with the model kit? Reasonable? If we get rid of the model kit, think back to Monday. How hard was that to deal with? How hard was that to deal with on the quiz? Okay, pretty hard. If you've got a model kit, it becomes infinitely easier, because now instead of trying to envision or pretend that you can envision a three-dimensional model from a two-dimensional drawing, manipulate it in 3 dimensions in your head, and then try and draw it again, it's already there in front of you. All you have to do is spin a bond, flip the structure, rotate, and draw what you see. Okay? The models make it infinitely easier to do. Okay? I highly, highly recommend you buy one. Okay? You can rent them from the stock room. They aren't these nice ones, but they are available, so you can pick those up as well. Okay? So one of the things that we further evaluated when we went through and talked about this yesterday, so we could add in our energy, our staggered conformation is lower in energy than our eclipsed, because we've given those bonds more breathing space. Okay? The example that we've picked so far is a relatively simple structure. What compound have we got drawn here? Okay. Remember, if we have a model kit, what we're looking at is those overlapping, and we turn it. How many carbons do we have? 2 carbons. The rest of those, hydrogen. So what compound do we have? Ethane. There's no interpretation of what do those lines represent, shifting where they're aiming. It's already done for you in the model kit. Okay? The model kit makes that vastly easier. If you don't have the model kit, which you should always have because you'll be able to rent it from the stockroom, and I let you use them on the exams. Okay? But if you don't have one, you need to be able to start to treat these two-dimensional drawings as three-dimensional structures. Okay? And that gets a little bit trickier to deal with, but let's go ahead and attempt that. Let's pick this red dot as our front carbon. And what I'm going to do is drag that carbon to the right. So it's now in front, and I'm pulling it sideways. Okay? So now what I've done is just rotated the structure. If I rotate that structure, my red carbon is now on what side? I'm going to try and make sure I'm looking at it the correct direction. What side of the molecule? The left or right side? Be on the right side, so there's my rightmost carbon. Okay? Just for the sake of, making sure we're looking at everything correctly, we'll look at our blue back carbon. Where's our blue back carbon? Right or left? Should now be on our left-hand side. Those would be connected by a bond. Okay. If we look at our red carbon, where is... I'm going to run out of colors, but we're going to do it anyway. That green hydrogen. Okay, if we pick it up and just rotate directly across, straight up and down, it's not coming at you, it's not going away from you, it's in the plane of the paper. If we want to represent the three-dimensional or the tetrahedral structure a little bit, okay, it's not coming directly up, it's going up and a little bit to the side, right?
So we tilted on there to just not overlap?
Yeah.
The hydrogens? Okay.
Okay, so we could now draw our rightmost hydrogen going upwards. Okay? We represent that it's being in the plane of the paper by doing what?
Solid line.
Solid line. No wedges, no dashes. What about, let's make sure I'm drawing the right one. Let's pick, crap. Now I gotta make sure I visualize it right. This one here. That's going to be coming towards you below our structure. So there's our hydrogen. What about that one? Below, but away. Okay? We can go through that same logic with the back carbon, and we should end up with something very similar looking. Okay? Kind of makes sense? You'll notice that method takes a lot of time. Okay? The only reason it takes time is that we aren't comfortable with dealing with these things in 3 dimensions inside our head. So go through and manipulate them with the model kit until you're used to it, and then you don't have to use the model kits anymore. What? Wow, it really does. Like, that's... Okay, I didn't want the drawings anyway. Okay, please start working again. Okay. If we go through and make our structures a little bit more complex, instead of dealing with just pure ethane, I can go through and change some of those hydrogens. If I only change one atom, okay, one of those hydrogens over to, say, maybe a methyl, okay, I don't get any new interactions. I'm either staggered or eclipsed all the way through. Okay? If I add two new groups at different positions, I can end up generating some new staggered conformations and technically some new eclipsed conformations. Okay? We aren't concerned about the eclipsed conformations because they're so high in energy that we aren't going to evaluate them anyway. So we'll look at our staggered conformations. Okay? And if we look closely enough, you can see the groups I've added are right here. Again, we're still staggered, but are those equivalently low energy? Okay, no. If we're adding any other atom than hydrogen, our size by definition must get bigger. If it's bigger, there's more electrons present. Those electrons want more space. We're going to try and position them as far away as possible. So in that first case, those atom X's are too close to each other, they're going to start to repel away. So if we're going to rotate, which one did I rotate? Rotated the front X, it's going to start to rotate away from atom X. Okay? In the process of rotating, eventually it'll reach a position where it's gotten as far away as possible, it's gotten as much space as it can possibly get. If we continued to rotate, we're ultimately just bringing it right back just on the other side. Okay? So we end up with these two new possible conformations. Because these are fairly common, these get their own names. You get gauche, you get anti as far as the names go. Okay? Kind of makes sense so far? Okay, one more little thing on practice. Let's try and draw the gauche conformation. I'll let all of you work on that, see if you can get that drawn into the wedges and dashes, or what I've been calling the line angle format. So go ahead and attempt to get that drawn on your own. If you've got questions about it, raise your hand. I'll come around and help you out. What we're trying to draw again is our gauche conformation. See what you can come up with. Okay? And I pulled that towards the right-hand side. As I do that, okay, sometimes I'll use my hand. X is now my thumb, and as I rotate it, X is now aimed away from me, so I'll show it with a dash. The hydrogen is aimed at me, so I'll use that with a wedge, and then the other one, or the other hydrogen, is going to have to be in the plane. You can go through and use the same logic with the other, where with the back carbon, okay, if we take a look at our hydrogens aimed down, in kind of that triangle, and we do that rotation, they're aimed wedged and dashed. Atom X ends up being in the same plane of my paper. Okay? So after we do the rotation, our plane of paper runs right through here. There's our paper line. Okay? Kind of makes sense?
As long as you have the going away, this X and the wedges, the hydrogen, it doesn't matter which side they are from each other, right? As long as they're above.
Technically, no. Okay. Where some of this can come in and be a problem is if I specifically tell you to draw this structure, you need to be able to draw it exactly as it's shown. If I say take that front carbon and rotate it to the left, draw exactly what you would see. If you start drawing something else, even if it's the correct drawing or the correct structure, okay, it's not what I asked for. Okay, so make sure you answer the question that I'm asking. If I give you those specific details, make sure that you include those details in your answer. Okay, kind of makes sense? Okay. This can be used or made a little bit more complex when we look at butane. Okay, so we added Atom X in this case is now a methyl group. And we could go through and start to plot the energy of each of those Newman projections. So in the case of what this drawing started with, is we decided to pick butane and start with it in the eclipsed conformation where our methyl groups and our hydrogens all overlap. The methyl groups being the largest groups, that's going to put us at the highest energy. We're already at a high energy because it's eclipsed, but then we've overlapped our largest groups. So if we were going to try and draw out a rough energy diagram, we could say we're going to put that structure or that energy representation at the highest point. What we then do, in the case of what they decided to do, is they rotated the front carbon. So they took that front carbon and they rotated it to the right, is what it looks like they did. Okay? When they do that rotation, you end up at the next structure. Okay? We're now at a staggered conformation. Staggered conformations would be lower in energy. So if we were going to draw on our graph, okay, or draw an energy representation of it, it would have to be a point that's lower than where we started. Okay? At this point, we don't know anything else, so we could just continue with as we've got, and we can rotate that one further. Okay? When we rotate it one further, we end up at another eclipsed conformation. So again, the energy needs to spike. Should it spike as high as our initial conformation? No, because the methyls are a little bit further away from each other. Okay? We've given them more space. It's going to be a little bit lower in energy, and that's why we see our peak a little bit lower. As we continue to rotate again and again in each of those cases, you'll notice that the energy changes accordingly. Okay? So when we get to the middle part, we end up drawing, again, a staggered conformation, which is low in energy. That conformation should be lower than our first staggered. Why should it be lower? Okay? We've taken our methyl groups and we've put them as far away as we can possibly get them. Okay? This is one of the reasons why we come up with those names, anti-gauche, staggered, and eclipsed, all of those fun things. It's because we're looking at different energy states. The gauche and the anti are different enough as far as their energy goes that we call them something else. Okay? Yes?
How come the gauche and the eclipsed, how come the gauche is lower than the
So when we look at the gauche, probably can't see that super well. So we can kind of highlight it.
The gauche is at least 60 degrees between.
Yep. Yep. When we go through and look at just the lines that I drew in there, the red and the orange, are we in staggered or eclipsed? We're staggered. When we move to the eclipsed conformation, which ones did I do? I did orange was in front. Versus our red. Are we in eclipsed or staggered? Eclipsed. Which means, which one should be higher in energy? Our eclipsed. It just so happens that our staggered conformation is a different staggered conformation than our lowest energy, and that's why we call it gauche. Okay? Gauche and anti are staggered conformations. Okay? They are the exact same thing. All we're looking at is a slightly different energy level, and because it's a different energy level, we give it a new name. Okay? Does that kind of make sense? Okay. Is that a question?
Yeah.
Okay.
So the bonds from relative to the carbon are always going to be 108 or 109.5 units in the tetrahedral. But when you're looking at it in this plane, in the Newman plane, they're 120, right?
Yes.
Okay.
I see what you're saying. So yeah.
Because the 120 isn't accounting for the third dimension.
When we look at that angle there, so now I'm not trying to highlight the back thing. If we look at the bond angle between those, right? If we look at just strictly geometry, ignore whatever's drawn behind it. So let's take it even further. Let's go out into some plain space. What angle am I approximately attempting to draw there? That looks like 120 degrees. If we go back to our structures, what's the bond angle between there? It's 109. Okay? Your Newman projection, while it attempts to incorporate some three-dimensional structure, can't draw in those wedges to account for that 109-degree angle. So the Newman projection takes a three-dimensional structure and condenses it to two dimensions. Everything you do in this class takes a three-dimensional structure and converts it to two dimensions. So regardless of what you're drawing, the bond angle is not true. So if I was going to draw a tetrahedral carbon atom, we can pick up in that back corner or that upper corner again. Okay? We could go through and say, yep, this we've decided is a tetrahedral carbon with what bond angle? 109.5. You're telling me that in my drawing, the angle right there between that dashed and that wedged is 109 degrees? Okay. My two-dimensional drawing is not going to show 109 degrees. My two-dimensional drawing gives me the interpretation that allows me to realize that it has to be 109. Okay? Does that make sense? So a lot of the projections in the drawings we use are to try and do our best interpretation of the two-dimensional drawing as best we can. Okay? Does that make sense? Okay. Kind of related towards the quiz, because I think I'm out of Newman projection slides. Yep. Okay. Are you going to go back? No. Okay, so when we're looking at Newman projections, a lot of the questions that you might ask, or I might ask, would be draw the Newman projection for such and such compound. Okay, like I did on the quiz, 2-methylpropane. Invariably, I don't think I saw anybody go through and attempt the problem the way they should have. Okay, and any of these drawings that we just went through, how many of them did I give you the name for and expect you to draw the Newman projection directly?
2.
Which one did I give you the name for and said, give me the Newman projection?
You said something 2-methylbutane?
I said 2-methylpropane from the homework, or from that quiz. Okay. So none of the examples we walked through went from the name to the Newman projection. Why? Because it's ridiculously hard to see. Okay? Don't try and convert from a name into a new projection, because that's going to be a difficult transition to do. Convert it into something that's easier to understand. So 2-methylpropane, you should draw out, at very least, a crude line angle. So if we've got 2-methylpropane, we start right to left, ane ending, meaning all single bonds, prop. We've got a 3-carbon chain. You had to do that, didn't you? I'm just going to draw it on here. We've got a 3-carbon chain. Is it showing up there? Yep. And highlight it a little bit. 2-methyl means at position 2 I have a methyl. So I can count 1, 2, there's a methyl. Now that I have a line angle drawing, I need to attempt to convert that into a Newman projection. Okay? A lot of the Newman projection questions you'll see, you'll have a reference. Say, look down the carbon 1-2 bond, or look down carbon 2-3. Didn't ask that for this, didn't provide that information in this case. Why? In a Newman projection, you look down an individual carbon-carbon bond. Which carbon-carbon bond in here is different from any of the others? None. They're all the same. It doesn't matter which carbon-carbon bond you look down, you'll get the correct answer. Okay, which is why that information wasn't provided.
So, for the homework,
Yes.
do you want us to draw, because I just drew these, but then do you want to flip the other way with the other ones in front, or does it matter?
So what I asked for was all essentially unique Newman projections. So let's go ahead and take a look at one. So let's pick a front carbon. What should our front carbon be? Tell me where you want it to be in that structure. Top, left, right, middle. I think I heard middle. So that's going to be our front carbon. Okay? What things are attached to our front carbon? Carbon, which carbon? Top, right, middle? Left. I didn't say that, did I?
Left top and then another hydrogen.
Okay. So we've got, running out of colors. Okay, so we got those three things. So we could try and draw those three things on there. Okay, and what you need to be careful of, so we go, okay, the three things are there, so let's draw those three carbons. Except, in a Newman projection, we're looking down a carbon-carbon bond. One of those carbons must be my back carbon. Okay, so which carbon do we want to be the back carbon? What'd you say? It's dark green, blue, or orange? Orange, thank you. There's our back carbon. You'll notice, a couple people said their circles look terrible. I'm not the best example either. Don't worry about it. Okay? So we're now showing a bond between carbon green and carbon orange. Where's that bond? It's hidden behind carbon green. Okay, so we can't see it. We should go through and specify the other bonds attached to our green carbon. At this point, we can draw any which bonds we want. Okay, so it doesn't really matter. I'll pick that kind of Y shape. Where's carbon dark green? On top. Does it matter? No. Where's carbon blue? Left or right? What's that last bond?
Hydrogen.
I don't see a hydrogen. It's implied. Okay. We do have an implied hydrogen there. We would have to make sure that we show that. We would specify by saying hydrogen. You'll notice also, yeah, that was a bad color to pick for those bonds. Should have picked green. Okay. You'll notice also I've drawn those lines fairly extensive outside of the ring, or outside of that circle and back, because I want to try and make it as clear as possible that those green bonds are going to the middle carbon. They aren't attached to that back carbon. And if I draw the lines just up to the circle, I'm going to lose track of what each thing represents. It's going to be more difficult to interpret later. I can then go through and draw the atoms attached to my orange carbon in back. What atoms are attached to the orange carbon in back? We've got 3 hydrogens.
Wouldn't you have 4 carbons then with the blue, green, the green at the top, and the orange circle? And you're only, it's pro, so.
Oh, there's a methyl attached to the protein.
If you move to a butane, then I'd have to specify what bond I want you looking down. Is that kind of what you're asking?
I thought with the Pro-B I'd had 3 carbons. And when you had it drawn, the circle would count as 1, and the middle would count as a dot would be 1. And then
Shouldn't have erased it yet, should I?
that would be 4.
So let's go through and highlight our carbons in
So
red.
why wouldn't you do a hydrogen at
There's
the top?
1, 2, 3, 4 carbons. All 4 carbons are in that drawing.
But aren't we doing
We are doing propane. We're doing 2-methyl propane. How many carbons are in 2-methyl propane? There's 1, 2, 3, plus our 4.
Okay.
Okay? Kind of makes sense?
Can you give an example of the moving down? Which carbon we're looking at?
For butane? Yeah. Let me clear actually where I got some space to draw.
Is it always implied that it's going to be staggered?
Depends on the question.
When you give us a name like that?
The question, it still depends on the question. The question I asked was provide them all. I would draw the easiest one for me to draw personally. The easiest one for me to draw, staggered. Everything's away from everything else. I've got it all nice and easy to see. Once I've got it nice and easy to see, then I'll confuse things by making it staggered. But I'm not going to start in the confused looking structure first. Okay? So let's take a look at providing the highest energy conformation for butane. How would you start? Okay, we can go through it, break our name down. We've got the A and E ending and our bute to begin with, which means we're looking at a 4-carbon chain. We could draw out a formula, CH3, CH2, CH2, CH3. Why do we not do that? Formulas suck. So we could draw something along those lines. Okay, it's also a whole lot less work to draw that than it is to draw CH3, CH2, CH2, CH3. Okay? The question I would then ask is, instead of just saying provide the Newman projection for it, because that is going to lead to a billion different answers for me to grade, is I'm going to say provide the highest energy. I said highest energy, didn't I? Highest energy Newman for the carbon 2, carbon 3 bond. Okay. So now that we've got our line angle drawing, we want to make sure that when we convert this into the Newman projection that we're looking at the correct bonds. Where's carbon 2 and carbon 3? In the middle of our structure. So I would probably highlight those, circle those, so that I know that that's where I'm looking. Okay. The next part of this, depending on how picky your grader would be, which would be me, and that's not very picky. If I said highest energy Newman C2, C3, that means C2 would be my front carbon. So we'd have to be very particular with how we drew that out. Since I don't really care, and as long as you're looking down that bond, I'm happy with it.
They're symmetrical.
Okay. This case it's symmetrical, yes, but not all cases. So what we now need to do is try and convert this into a Newman projection. Okay. So I would pick my center atom. Okay. As with all Newman projections, we either get that Y shape, or get that antibody shape. You either get the Y or the upside down Y. I would add that information into it, just for the heck of it. Okay. Let's go ahead and call that back carbon green, just so it stands out a little bit differently. So I want to evaluate what things are attached to that red carbon. So what do I have? I have a CH3 and 2 hydrogens. Why did I not draw the green atom in this yet? Because that's going to be the one in the back. Okay? You'll notice also when I go through and draw that back circle, I usually draw it so that my red lines or my front atom lines are in front of it, so there's a clear line between it. That's just, again, as a way to help me recognize which atoms are in front, which atoms are in back. Go through and do the same reasoning on the back one. I want to go through. Again, for me, the easiest is a staggered conformation. Okay. What atoms are attached to that carbon? This would naturally be the Newman projection that I would gravitate towards. Okay? So if we immediately drew that out, great. That is a phenomenal Newman projection. Does it answer the question? No. It asks for the highest energy Newman projection. So I'm going to have to adjust my Newman projection to account for that. Now I would go through and try and answer the question. I'm going to pick one of those carbons to be stationary. I think I like picking the back one to be stationary. So I'm going to draw that one out, fix it in space, and now I need to rotate the front one. Okay, for it to be highest in energy, do I want staggered or eclipsed? Eclipsed. Okay, for it to be highest in energy, where should my largest groups be? As close to each other as possible. So to do the eclipsed, I'm going to go through. I did a terrible job drawing that, but you get the idea. You can draw the CH3, hydrogen, hydrogen. I've now answered my question. Just to be extra sure, I might box it in, being nice to the graders so they know what answer to grade. Okay? Does that make sense? Okay. You still need to be comfortable with going the other direction. So given a Newman projection, you need to be able to convert that into the line angle drawing. If we converted our Newman projection, would it look like this one? Would it look like the line angle drawn here? The same compound, but is it the same drawing? No. What would our drawing look like? Okay. That would be our line angle representation for this Newman projection. Okay, where those methyls are now in the same plane, which is why they're in that solid line, and they're both aimed in the general up direction. Kind of makes sense? Okay, we will make it more difficult here in just a second. So let's take a minor break away from Newman projections and look at cyclic structures. Your textbook goes through a whole bunch of explanations for them. This kind of summarizes everything with it. I don't feel like going into a lot of detail with each of them. Okay. As we move through these, we talked about some of the nomenclature issues. You pretty much just add the cyclo in front, keep everything else relatively similar. Some of the repercussions comes down with this last line that's now empty, is the stability section. Okay, stability or reactivity. Which of these would I predict to be more reactive? Propane, butane, cyclopentane, cyclohexane. Which of those cyclic structures would you expect to be more reactive or less reactive? I can accept either answer. Cyclohexane would be the most or least? Least what? Reactive. Don't quite want to get that far, but pretty close to it. Take a look at our carbons in cyclohexane. How many electron groups are there, or sigma bonds around that carbon? 4, which means the hybridization is sp3, which means the bond angle should be 109.5 degrees. What's the bond angle in a cyclohexane? 109.5. That sounds reasonable. Okay, that makes sense. Let's move to cyclopropane. How many sigma bonds around that carbon? 4, which means what hybridization? Which means what bond angle? 109.5. What is the bond angle in a cyclopropane? 60 degrees, which is ultimately a triangle. Okay, equilateral triangle, that's the bond angle there. Does that carbon want to have a 60-degree bond angle? Why not? The electrons are too close. They want to spread out to that 109.5 degree. We've forced them closer to each other. Okay, what does that ultimately mean about the reactivity? It's going to jump up. What does that mean about the stability? It's going to get lower stability. Okay, so we would expect the lowest stability for our cyclopropane. And we end up increasing generally or pseudo-linearly until we get to the highest stability for our cyclohexane. Okay? And that's a result due to a couple things. The easiest one to make or reference would be the internal bond angle. Okay? The other thing that we could reference, which I'll leave you to do, if you've got a model kit, you can do it with the butane and with the cyclopentane, would be look at the model kit, add on all those hydrogens, and look for a Newman projection. Okay, so pick any carbon-carbon bond, and look down that carbon-carbon bond at the Newman projection, and tell me which conformation you've got. Any guesses as to which one you're going to end up with? It's eclipsed. And all of those structures, your propane, butane, and pentane, if you look down the carbon-carbon bonds for your Newman projections, you end up with an eclipsed conformation. How stable is an eclipsed conformation? Not very stable at all. Okay? So maybe, or what we would expect is the structure to alleviate it. So when we looked at, say, our ethane, what happened when we were in an eclipsed conformation? It rotated. That's nice. Let's take it to propane. Let's not take it to propane. I don't want to break my face. Let's take it up to butane. But not with any of those. And if we're in a cyclobutane structure, come back here. We look at that Newman projection. What's the relationship between our bonds? They're eclipsed. Okay, not a particularly stable thing, so what does the structure like to do? It wants to rotate that single bond so that we can actually alleviate that eclipsed conformation. So let's rotate. Maybe the other way. Can't physically do it. Right? So these structures, your cyclic structures, even though we have sigma bonds, can only rotate so much. And you'll notice as we add more carbons, we can start to increase that rotation. If you go all the way to the cyclopropane, okay, you won't be able to rotate any of those at all. With the cyclobutane, you can get a slight pucker to your structure, and if we look at the Newman projection and that slight pucker, you'll notice it's not exactly eclipsed. It's ever so slightly askew. For some reason, they come up with another name for it. I don't even know what it is. It's not all that relevant. Okay? But we do see some of that adjusting. Okay? So your rings have a couple primary side effects. The smaller they are, they tend to be more reactive. Okay? They're prone to react and open up the ring as fast as possible to alleviate some of that angle strain. It also helps to alleviate the torsional strain coming from the eclipsed conformations. Okay? Cyclohexane is a special case. Okay, so most of this chapter is pretty much devoted to trying to find an explanation to start discussing cyclohexanes. Okay, so let's take a look at cyclohexane. Whoa. Okay. So let's take a look at cyclohexane. We end up with a whole variety of different viewpoints on our structure. Okay, so we've got a couple different ones shown here. We can go through as we would abbreviate in most cases, and you would probably think about cyclohexane as in that red box. 6 carbons all connected. We imply all the hydrogens so we don't have to worry about them. Okay? If we were to put that together and not imply the hydrogens, each of those carbons is tetrahedral. So to show that three-dimensional tetrahedral nature, we would need to include wedges and dashes. So we can add some more information to it and show the wedges and dashes on all the hydrogens. Okay, really, really tedious. Okay? If we want to take that a step further and start to evaluate, is there a difference in energy for individual structures? That's where we start to move into chairs. Okay? I can go ahead and add a couple more carbons to this so that we can get a chair put together. Okay? Oh, get in here. That's fine. So, we take our model kit out with our 6 carbons, and we look at it from the overhead view. Okay, particularly if you blur your vision, that tends to look like just the hexagon. Nothing particularly fancy about it. Okay? Particularly if you get really blurry vision with it, maybe take out your contacts or something like that. You don't see anything coming at you or away from you, it's all nice and flat. Okay? Then we decide to get real tricky with it. How flat is that structure? Not very flat at all. Okay? When we go back and now start to evaluate our sigma bonds nature, okay, what did we say was special about sigma bonds? They could rotate. So just like with our cyclohexanes, we're now going to take, or as we attempted to do with our cyclobutanes, we're going to attempt to do the same thing with our cyclohexanes. Can we rotate? Notice we do get a reasonable amount of rotation. We can't get a complete 180-degree rotation, but there is a reasonable amount of rotation between those two. Okay? Because of that rotation, we start to see some things change as far as energy and different dynamics. Okay? So the first thing that we're going to do, this conformation that we're looking at here happens to be one of the more stable conformations. In fact, the most stable as far as we're concerned at this point. Okay, let's get rid of these bonds. See if this can help you visualize what's going on here. What does that shape look like? Okay, so first off, well, there's a couple of fun answers we can go with this. It starts to look like what I've got drawn up here. Okay. All someone went through and did is built the model and said, okay, now I need to draw that as best as possible. And in the process of trying to draw that out, that's what they drew. Okay? Then somebody who probably didn't have any chemistry knowledge happened to look over their shoulder and looked at it and said, hey, that looks an awful lot like a chair. They were cross-eyed too, maybe. Okay? Where's that chair? Well, if we take a look at the chair drawings that we've got up here, we've got the back of our chair here. We've got a place where we could sit down in the middle. So there's our seat. And we've got a place where we can relax our feet. Okay? One of the things that's a bit difficult with this section of material is all of it comes down to being able to visualize the model in the correct fashion. Or in the fact that it's not even the correct fashion, it's in a certain fashion. So that when I talk about it, I know that you're seeing the same thing I'm seeing. Or that when you ask me a question, I need to know exactly how you're looking at the molecule. Because if you're looking at it from a different perspective, you see a different chair. For instance, okay, what I've got drawn here right now looks like which chair? Right or left up there? Where's the back on this chair? My right hand or left hand?
Your right hand.
My right hand. Which would be which chair?
The left.
It looks different from here. It's hard to tell which side is up.
Okay. So half the class is saying left. So let's try and move over here now.
Now it's left.
Now what's it look like? Your view has changed on the individual model kit, which means you're seeing a different chair. If I turn and rotate it here, you can find yet another chair within it. If I rotate it here, you get another view of a different chair. Each of those rotations is the same molecule. Depending on the question, you may answer it wrong because you're answering a different question than what was asked. So you have to be very careful about what structure you're looking at in each case. Okay? We'll look at an example here in a second. But the next thing, just because it's fun to look at Newman projections, so we might as well. We can also take our chair, or take our cyclohexane, and instead of looking at it from the side or the top, we can look at it, hopefully I don't break it, okay, in a Newman projection. So if you look at my left hand, you see the Newman projection? What Newman projection do we have there? It's staggered. Our bonds are all in empty space. Okay? We said the chair was one of the more stable conformations. Why would the chair be one of the more stable conformations? Because in our Newman projection, we're in a staggered conformation. Okay? If we were going to draw the Newman projections, you'll notice that you have two Newman projections next to each other. As I've gotten the model kit set up, we can really only see one, but if you add the bonds to the other side, you get another Newman projection. Okay? So those Newman projections are tied to each other. So if we take a look at this projection, as you guys are looking at it now, which one of these structures shows it accurately? Left or right? That's the confusion. Left or right? Okay, now I know the answer.
Which way are you going?
That's what I'm trying to figure out now. So from your view, which is the correct Newman projection? This one here. This CH is down below the plane of my seat. It's also attached to the front carbons. If we take a look at my front, oh man, it overlaps some bonds. Crap.
It's overlapping the hydrogen.
That bond should be to the back carbon. I'll have to fix that so you can see it a little bit cleaner.
The other ones are all that.
Yeah, I know. I'm going to have to fix that so you can see it a little bit better. If you look at the CH2, you look at the left half of it, the CH2 that is down, okay, is attached to the front carbon here. If we take a look at the CH2 that's down on the left side of the Newman projection, right side of the Newman projection, right side? No, that's left side, isn't it? Man, on the left side of the Newman projection, where's our CH2 attached? It's attached to the back carbon. That's not this conformation. Okay? Does that kind of make sense? I'll fix the Newman projection drawings for the next presentation so you can see that a little bit better. Okay? As with all things organic chemistry, one of the first pieces of advice that I will give you for pretty much anything will be to draw. Come on. Yep, that's what I figured. I'm going to have to wipe some stuff, see if I can clean this up. We want to draw things. You are going to be required to draw out cyclohexanes and draw them in a way that I can grade them. Okay? If I ask for a chair drawing and you draw me an overhead view, you don't get points. Okay, so you have to be fairly clear with how you put these things together. Okay? So this is a general guideline for how to start it. I recommend personally starting with the seat of the cyclohexane. Okay? So we'll pick two angled lines. We'll draw them roughly on top of each other. We can give them a little bit of space in between them and kind of staggered. So that when I draw this out, we draw something along that and that. Okay, so you notice we've got a staggered situation there. I'll then go through on either half of that molecule, so I'll roughly cut this thing in half, start to either half. Whichever one was the short side, that's where I'm going to start drawing my next line. Okay, so if I start on the left, my short side is now, okay, we'll now start right there, and I'm going to draw a bond angled up and away from it. Okay, I'm now going to connect that to my bottom one. We'll move to the other half of the structure. Again, I'm going to pick the short side, and I'm going to draw that angled away from my longer line, which will be down, and then connect. There's a chair. You'll notice on that last slide I had two chairs. One faced left, one faced right. Okay, so we need to be able to draw the other one too. How would we draw the other one? Stagger the lines the other direction. Which I almost always screw up, so let's see if I can do it right. Stagger the other direction. Again, up, down, down, up. My chair is now facing that direction versus that direction. One of the things that you'll quickly notice when trying to draw out drawing out your chairs is you'll draw one inherently better than the other. Okay? Based on my interpretation, I think I can draw the top one a little bit better than the bottom. Okay? A little bit better. Okay? Takes a little bit of practice getting used to putting them together. Once you get comfortable with it, it should go pretty fast. Okay? We now have a cyclohexane. The next fun issue that I can't click through Okay? Are all the positions on our cyclohexane created equal? So what do I mean by that? So here's our chair, our cyclohexane. If I compare this green bond to this green bond, do they see the same things? No. Okay, well this one's aimed, they're both aimed up, but this one's aimed kind of out away from the side of the structure, right? Off to the side. Where's this one aimed? Straight up and down. Uh-oh. What does that mean? We've got two different positions on our cyclohexane. We need to be able to identify those two different positions, decide between them which is more or less stable. Okay? Okay? Those two positions are referred to as axial and equatorial. You need to be able to draw those clearly on your cyclohexane. So let me draw out a cyclohexane again. I'm going to do this guy. Each of those carbons technically has an axial position and an equatorial. Our axials are always pointed straight up and down. Okay, so if we're going to try and draw in our axial positions on this cyclohexane, we'll pick a carbon. So let's go ahead and pick, say, this carbon. It's easier. Our bottom right carbon. I've got two ways that I could draw, up or down. Which way should my axial position be? Up or down? Okay, let's go through and take our model kit. Right? See the chair? Where's our axial position?
Down.
Aimed down. Where should we draw it on our structure or on our line angle drawing? It should be drawn down. Where's our axial position for that next carbon? We go up here. Up or down? It's going to be drawn up. How about this one? So we're continuing around the ring. We draw it down. How about this one? Noticing a pattern maybe? We started down, we went up, and then we went down, up. How about the next one? Down, last one, up. Okay? One thing that I usually recommend that I feel helps as far as deciding where to draw up or down, look at the triangle point from your carbon. So let's highlight that red carbon. What do I mean by the triangle point? Look at the bonds leading to that carbon. Where is that aiming? Up. Where should my axial position be? Up. Okay? If we look at all of those triangles, you can identify which is up and which is down as far as where you should be drawing your axials. Equatorials are a lot more difficult to identify, and in general, what I would recommend is just not drawing them axial. Okay, which sounds kind of obnoxious, but it works fairly well. Okay, so if we pick, again, our tail carbon here, okay, where was our axial? Down. So, where's not axial? We could start pointing up. Okay. How about the next one? Point down. Notice I'm not putting it directly down. We'll come back to that in a second. How about this one? Okay, there's all our equatorials. Most drawings, if you look really carefully at it, your equatorial is parallel to the second bond away. So let's go through and show that in green. So there's our equatorial position. We're trying to identify where to put it. Let's count out 2 bonds away. There's 1 bond, 2 bonds. When I draw on my equatorial, you'll notice it's roughly parallel to that. But let's say I don't like counting that direction. Let's count the other way. 1 bond, 2 bonds. Huh. Still parallel. Okay? That will help me as far as grading goes, which means you'll get more points. Be aware there's an even more clear way to specify it. How would you do that? Wedges and dashes are not a bad idea, except if you add wedges and dashes to now this already confusing drawing, it's going to be a bit of a mess. Okay? Particularly if we're going to look at this position. Is that wedged or dashed? Right here. Coming at you or away from you? Ooh. Okay, yeah, which way are we looking at? So the wedges and the dashes aren't going to be the easiest things to use. Our cyclohexane, our chair conformations, already imply three-dimensionality. Okay, so we don't want to confuse them even further with wedges and dashes. Which one's axial? How about the one that I labeled as axial? Okay, so when in doubt, label it. That way it's clear. If I don't like the way you've got it drawn, for instance, if you swap the axial and equatorial labels, I'll probably give you points because you know you were probably able to answer the question correctly, but you drew it terribly. So you get most of the points, but you'd probably lose some because you just drew it way wrong. Okay? Kind of makes sense? That's why I don't have backpacks in. So that is the end of time, first off. So if you need to take off, feel free to take off. Let me go through and pick another equatorial. Let's see if I can back out some of these green bonds. Okay, so let's pick a different equatorial position. Let's pick this one in green. So what we're trying to decide is where to draw that line. Should we draw it where it is, or should we draw it some other angle away? Okay. So our first rule is don't draw it axial. Our axial is aimed straight down. Don't draw that one anywhere remotely on this side of the structure. Okay. The next part is trying to figure out the exact angle on where you drop that line. The second bond away. So we're looking at trying to draw our equatorial around that carbon. So we can count out 2 bonds away. 1 bond, 2 bonds. This second bond, which I'll now highlight in orange, is parallel to our equatorial position at that carbon. If we count it the other direction, there's 1 bond and 2 bonds. Our second bond away, again, we're parallel to that bond, roughly. Does that make sense?